Okay. So the first thing I'm going to do is we're going to look at the function like that. A times, I meant to do a B there. That's the way they do it. A times B to the X. And so I'm going to make a slider here. And so what I've done is I've created this function f of x, that's function notation, is equal to this number a. And right now, a is set to a value of 1. You can see that a equals 1. So, and then b times b to the x, and b is currently set to 1 as well. And notice that it's just this flat line, it's a horizontal line, and where x, as x changes, the y value stays 1. Y is always 1 along this line, and you can see all those points right there. Now the important thing that is going to change is when we change the value of b. So I'm going to put in just 1.1 and check that out. So now it changes into a totally different shape. This, we know a shape like that, it's known as an exponential curve. And that's because the variable is in the exponent. So exponential functions have the variable x in the exponent. And watch how the shape changes when I increase the value of b. It gets steep really fast as I change the value of b. And this is when b is between 0 and 1. Look what happens. Okay. And then when b is negative, it doesn't do anything. It doesn't work. Okay. So this is exponentially decreasing because as we go to the right, the y value is decreasing. This is exponentially increasing because as we go to the right, the y value is increasing. Now I'm going to put this to 2 because that's kind of what we call the parent graph for exponential functions. And now watch what happens when I change the value of a. Does it look like it's getting steeper? Yeah, but also there's something changing that wasn't changing before. The y-intercept. So a is actually a y-intercept of 1, because this goes by 2's. The y-intercept is 1. So as long as we have a function like this, a times b to the x, the a value tells us the y-intercept. Let's see. So when the a value is 2, or when the a value is 3, the y-intercept is 3. Let me see if I can do something. Oh, yeah. Okay, there we go. So watch this. So as I change the a value, our y-intercept is changing. So far, does that all make sense? Okay, good, good. All right. Do you want to ask a question? The exponent is just the x value. So let's see, how can I show this? Let's look at x, f of x. And can I, doesn't like that. Let's see. Okay. Let me see if another way to say this. So right here, 5, when the x value is 5, the y value is 9.6. So let me see. Let's change this up. Let's put an a value of 1 and a b value of 2 and talk about when x is 3, the y value is going to be 8. And you can see it there. It's on the graph, but I'll show you why algebraically as well. And you may already see why, but so our function f of x, and I know you can't see what I'm writing right now. Let me fix that. F of x is equal to, well, the a value is 1, so I can write 1 there, and the b value is 2, and there's our function. Now, f of 3 says we're going to plug in 3 into the equation for x, so that's what we get. And then that's going to be 1 times 8, because 2 to the 3rd power is 8, and then 1 times 8 is 8. So that says that when our x value is 3, our output, our y value is 8. And so you're looking at the example in the book or in the lesson. It's the x is the input, the f of x is the output, the y. So so what it says here is does this come from the original? Yeah, okay. So you've won a contest and they can pay your prize in 2 different ways. One option is $10,000 every 10 days for 30 days. So you'd get $30,000, or a penny that double, you get a penny on the first day, 2 on the second day, 4 on the, excuse me, a penny on day 0, 2 pennies on day 1, 4 pennies on day 2, 8 pennies on day 3, so it continually doubles. So the question is, which one should you choose? So in this situation, the equation is actually this very same equation that we were looking at right here. But instead of f of 3, we're looking at f of 30 is equal to, I don't actually have to write that 2 in there, so I can, or the 1, excuse me, I can just do 2 to the 30th power. Now, that's a really big number. So what I can do is I can come over here and I can just type in f of 30. And so it's 1.07 blah, 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 blah times 10 to the 9th. That means we have to move that decimal 9 places. Wow. So let's just see what that would be. That's going to be 1, and then here's moving it 1 place, 2, 3, 4, 5, 6, 7, 8, 9. So that's how many pennies there are. So we have to divide that by 100 to see how many dollars. So it would be that many dollars. Hey, Ray, 10 million, I think. Did I option 2? Yeah, $10 million. So significantly more, but it seems hard to believe that just doubling creates that much more. It's pretty amazing. So the big takeaway message here is that exponential functions grow really fast, really fast. And you can see graphically how it just shoots straight up. And if we zoom out, so you just can't even see. So then we can maybe go in here and we can say, listen, our X values, we're going to go from -1 to, we only want to go to 30. We'll go to 31 and we'll do steps of 2. And our X axis, we're going to go from negative, probably going to need to be 10,000 in order to really see it, up to 11 million. And let's see how that looks. So now we can see that it seems like it's not even growing here, but then on day 16, it just explodes. That's crazy. So that's the power of exponential functions. So that's where you start. And let's talk a little bit more about some of this stuff. Let's see. Have we talked about the properties of powers? Like, I think we have, you and I have. Like, x to the 3rd times x to the 4th equals x to the 7th, stuff like that. Have we talked about that? Okay, I thought so. All right, so we don't need to talk about that. And have we talked about, I think so, where we have something like x to the power 2/5, that is equal to the 5th root of x squared. Have we done those conversions? Ray, do you want to stay here, or do you want to go to a breakout room, or should we go to a breakout room, or what should we all do? Are we good?
I'd like to stay here.
Okay. You're enjoying me my talking?
Yes.
All right. All right. So that's converting. All right, we did that. Great. Okay, so the next thing that we have here is it asks to find the equivalent form of this function. So the equivalent form of that function. So what that means is right now it's written with this 3 up here in the exponent. So it makes it kind of confusing, but we can change it by using one of the exponential rules, one of the rules of exponents. And here's how we can change it. here we have, whoop, that's too big. Here we have this 4 and this 3 up here, and that's kind of where the change is going to occur. So one of our exponential rules says, we usually think of it a different way. If we have x to the a to the b power, we can rewrite that as x to the a times b. And we often talk about going that way. But this time we're talking about going this way. So we have a, that's our 3. And then we have x, that's our b. So we can rewrite it like that. And then our in this case, our 4 is the x in this case. So we can rewrite that as 3 times 4 to the 3rd power, and then all of that raised to the x. Now we can say, all right, well, this 4 to the 3rd power is 4 times 4 times 4. And so we can just put that in our calculator if we want to, and we'll find that it's 64. And the bigger that this base gets, the faster this thing's going to grow. This thing's going to be growing so fast. So we saw that when this is 2, the base is 2, it grows really fast. But when the base is 64, it's just exploding. It gets big so fast. Here, let's have a look at it. So I'm going to change this to 2 to the x, and we're going to keep it there. And now we're going to have some other function g of x, and it's going to equal just 64 to the x power. And look at how fast this thing looks like. It's going straight up super fast. It's just boom, exploding. Way quicker. Yeah. Now, if I put in a 3 times 64 to the x, is it going to change it a whole bunch or just a little? What do you think? Yeah, it's just going to change it very little. Look at, let's do this. Let's copy this, and we're going to change it to h of x. So we have a new function and put in 3 times that. And look, it really barely even looks any different. So this, remember, is the y-intercept. So if we zoomed in really close on the y-intercept, we'll see that they cross the y-axis at a different spot. So let's do that. Let's go from -6 up to +6, and whoops, that's not what I wanted. Well, I can do this from -2 to +5, and do this from -2 as well. So here now we can see that that blue one, where we have 3 times 64 to the x, has a y-intercept of 0, 3. And the red one that doesn't have the a value there, the a value is actually 1, it crosses the y-axis at 0, 1. Hey, Skylar, welcome. Skylar, we're here just kind of chit-chatting about exponential functions. You're welcome to stay, hang out, and talk about exponential functions with us. I can put you in a breakout room if you would prefer that. It's up to you. Okay. If you'd like some help, let me know. I can come help you out as soon as we're done talking about exponential functions. Do you want me to come check in with you? Okay. There you go. All right, so okay, so now the next example we're going to look at is going to be a bit different. It's going to be f of x is equal to 5 times the quantity 1/2 to the power x. So what does this 5 tell us? Do either of you remember? What does the 5 tell us? Yeah, it's the y-intercept. So the y-intercept is going to be the point 0, 5. So we know that will be on the graph. Good. And what does this this value 1/2 here, that is the base, tell us? So yes and no. It tells you about something about how it increases. Yeah. So in this case, because 1/2 is between 0 and 1, we will have an exponentially decreasing function. So that means it goes down from left to right. Okay. So, anyways, yeah, let's go look at that real quick, and then I'll show you something else. So we had 5 times 1/2 to the x power. And so, yep, our y-intercept there is 0, 5, and we can see that it is decreasing exponentially. Now, what do you think happens if I put a 4 up here in the exponent? So it's 4x instead of 4. What's going to happen? Will it change the y-intercept? No, the y-intercept's still going to be 5. So what's it going to do? Let's see. Oh, it decreases faster. Interesting. So let's see why that's true. So let me see, how do I want to do this? I think I know what I want to do. All right. Okay, so now instead of I basically have the same function here, except that instead of x, we have 4x in the exponent. And now remember, we can rewrite this just like we did in the last one. We could rewrite this as g of x is equal to 5 times the quantity 1/2 to the 4th power to the x power. Now, I bet it's hard for you to think about, because it's hard for me to think about what this is. 1/2 to the 4th power. What does that mean? 1/2 to the 4th power. Yeah. Oh, nice way of writing it. Yeah. So when we multiply 0.5 by itself 4 times, is that number going to be bigger or smaller? So check this out. 1/2 times 1/2 times 1/2 times 1/2. Now, when we multiply fractions, we multiply across the numerators. 1 times 1 times 1 times 1 is 1. And across the denominator, 2 times 2 times 2 times 2 is 16. So what we can actually do is then rewrite this equation. Y equals 5 to the 1 over 16 to the x power. Is that bigger or smaller? Is this bigger or smaller than 1/2? Smaller. Yeah. Yeah. So whenever we multiply a fraction that is between 0 and 1 by itself, it gets smaller. Okay. So now we have this, the y-intercept is the same. That doesn't change. But now our base, which we also call the multiplier is now smaller in this new version, this new equation. So when we look at the graph, what do you think the graph, how is it going to be different than f? How is it going to be different when we do 1 divided by 16 instead of 1 divided by 2? It's going to shrink faster. Yeah, it gets smaller faster. Yeah. Good, good, good. Okay, so let's see what's up next here. So now, one of the big applications, so the places that we use exponential functions is related to their money. So interest, compound interest is exponential growth. Credit cards, also, that's like the opposite. You have to pay more. Credit cards are dangerous too, if you don't use them wisely. Another place that we use this is population growth. So lots of species grow exponentially, at least for some amount of time. I think that the population growth in India has been growing exponentially for a while. And now it's the biggest, most populous country in the world as of within the last year, the last few months, I believe. The decay of isotopes. So this may sound familiar to you from science. Yep. From science, we estimate the age, like how old things are from the distant past, from a long time ago. We use the isotopes to estimate how long ago animals were alive, especially when it comes to things like dinosaurs. So they use what kind of isotopes? I'm blanking. Do either of you know?
No.
Carbon. Carbon-14 isotope specifically. So yeah, carbon-14 is used to estimate things like dinosaur bones. When was the dinosaur alive? So these are the three most common places we find exponential functions: money, population, and isotopes. Okay. So when we're talking about money, actually, when we're talking about all of these, the general form of the function is is just the way they do it. Think like that. So again, as before, this is our y-intercept. It's also known as the starting value. Then b here, you have to convert it, but it is the percent either increase, whoops, let me see. When that's a plus, it's a percent increase. And when this is a subtraction, I should say addition, not a plus. When it's an addition, it's a percent increase. When it's a subtraction, it's a percent decrease. And then I think in all of these situations, X is going to be based on time, some amount of time that has passed from the beginning of the situation. Okay, so that's really the basic layout for understanding these application problems. Now, so notice that we're not writing them in fractions like we were before. The base was a fraction up here. It's nice to see the when that fraction's between 0 and 1, you're going to have a decreasing function. Excuse me, yeah, a decreasing function. When that base is bigger than 1, you'll have an increasing function. But now this is going to be a number with a decimal, and when it's bigger than 1, it'll be an increasing function. When it's less than 1, it'll be a decreasing function. Okay, so if we think about like a let's keep that there. When we think about something like a compound interest, so in the curriculum in Buzz, they use, for money, they use P for principal, that's the amount you start with, and R for interest rate, interest rate. So they use P and R. So for let's say money, so it's still important to know that we're still talking about a starting value when we talk about the principal. And it's the y-intercept still. That's not changing. But here now we're talking about the interest rate. And everything else is the same. Okay. Sometimes, very often, your X is time in months, but it can be different amounts of time. Okay. So if we think about a situation where someone invests when we're talking about an investment, then we're talking about an increase in money. Okay. Let's say they invest $100 at 3% annual compound interest. Well, if they invest $100, that's our principal. At 3%, that's our interest rate. And annually means that X is yearly. Annual means yearly. So in this case, our function is f of x is equal to 100. That's our principal, our starting value. 1 plus, because it's a it's an interest rate. We're accumulating, and it's an investment. It's going up. And we have to convert our interest percent into a decimal. And you know what the word percent means, right? What does percent mean? Percent. Yeah. So what it means is per per 100. Yeah. So it's saying, in the case of 3%, it's saying 3 100ths or 3 100ths per cent per 100. A cent, remember, is like a penny, a cent, and there are 100 pennies in a dollar per cent. So in this case, it'll be 0.03 or 0.03, same thing, and then to the power x. And let's say that that we know that we're going to invest it for 20 years. How much will we have after 20 years? Well, that'll be f of 20, which is equal to 100 times, and I'm just going to say 1.03. So I can take these, and because they're in parentheses, I can combine them together. And then it's easier to see, oh, I've got an increasing exponential function where my exponent now is 20. And I can't do that offhand. I need a calculator in order to do that. So I'm going to go in here and I'm going to make my function. F of x is equal to 100 times 1.03 to the x. And then if I want, I can just be real lazy and say f of 20. And it tells me that I will have, after 20 years, my $100 will have become $180.61. Now, does that seem like a lot? Yeah. 20 years, $80, not a lot. What do you think would happen if I changed this to 1.08? So instead of 3%, I were getting 8% interest. Will it double the amount of money? So it'll be 360 instead of 180? It won't double. What will it do? Will it be less than double, more than double? So yeah, an exceptional increase with 8%. Let's see. Whoops. It goes from 180 to 466. Yeah, that's a big difference. So why do you know why 8% is an important amount? Like, why would I bring up 8%? Whoops. Ray, do you have any idea? It's actually higher than I thought. I guess it's closer to 10%. So if you take the stock market, there's this thing called the S&P 500. Have you ever heard of the S&P 500?
You're muted.
Sorry, thank you. So the S&P 500, S&P stands for Standard and Poor's, and it's just this index of the 500 companies that are performing well on the stock market. And there's a list of the S&P 500 every year. And if you just invested your money across all of these 500 companies, on average, you'd have a return of about 10%. So instead of 8% here, it would be 10%. So, and look at the difference there. So at 3%, you only would end up with $180 after 20 years. But at 10%, you'd end up with 672. And what if instead of $100, we invested $10,000? Well, now you're looking at $67,274 after 20 years. And that's a lot. So compound interest, investing wisely in the stock market, can really result in a lot of monetary return. Now, an important part of this is you have to just leave your money there. You can't go in and be taking money out and stuff like that. So it's a really it's an interesting thing, I think. Anyway, so that's why we really talk about compound interest is investing money. Now, there are other kinds of things that are happening in our world that are less wonderful than compound interest on money, like a drought. So in the curriculum in Buzz, there's an example. Due to a drought, the water level in a pond decreases by 7% per year. Yeah. Well, what's really scary, Ray, is when your stock prices lose value. And let's say you go from having $10,000 worth of stock to only having $8,000 worth of stock. And it still looks like the market's going down. You have to leave your money there and trust that eventually it's going to go back up. And lots of people don't. So they end up losing money. But overall, across the S&P 500, if you leave your money there, it'll go back up, and then you'll start making money again eventually. So it's weird stuff. Psychologically, it's hard to understand. Yeah. In the past year or two, it's been pretty bleak. Things have gone down, the value of things. So if you have money invested in the stock market, you can lose a lot of money. Anyway, due to a drought, the water level in a pond decreases 7% each week. Wow, it's a lot. The pond started the summer at 12 feet deep. That little thing means feet. Create the function that represents the depth of the pond per week. Use that to find the depth of the pond after 10 weeks. All right. Okay. Do you know what the equation will be? How do we write the equation? Really close, really close. I'm going to show you the important thing that kind of slipped through the cracks here. So remember, it's 1 minus, minus 0.07 to the x. And then after 10 weeks will be f of 10, as you suggested, which will be 12 times the quantity 0.93 to the 10th power. So I just took that 1 minus 0.07 to get the 0.93. So we can see that it's decreasing. So whenever it's a decreasing exponential function, we're going to use subtraction here. And then this is going to end up being less than 1. Okay, so let's yep. It's a decreasing slope. It's not negative. So be careful there. It's a decreasing slope. We have a subtraction here. And then this is going to be 12. And so we can see that our y-intercept here is 0, 12. That's the starting value. And if we want to know after 10 weeks, we can see out here, we can see right there on the graph. There it is, 5.808. So another thing we could do is we could just do f of 10, and we would get it right there. So this is then equal to 5.808 feet. So if the pond started out at 12 feet and it loses 7% per week, that's a lot. Then after 10 weeks, it'll be 5.808 feet. Now, there's something interesting about exponential functions and how they relate to reality. Okay, so let's look at this exponential function. And okay, notice that here at 10 weeks, it was at 5.808. And as we go out here further, what do you notice? I'm going to zoom in now. Check it out. I'm zooming in. What's happening? Can you see what's happening here? Yeah. Yeah, the 10% of 100 is 10, and 10% of 50 is 5. So 10% of a very small number is a teeny tiny number. So it keeps decreasing by less and less. Yeah. So it never, ever, ever will reach a value of 0. So what that says, that in this situation, this pond will always have a little bit of water in it. No, eventually it'll just dry up. That's what happens. So these exponential functions in situations like this don't really make sense. Oh, I haven't been recording it, my friend. I could, I think it's being recorded by um Zoom, so maybe I could edit that video if you want. Yeah, I can do that. It's going to be a long video though. All right, I'll do it. All right, so yeah, and so what's interesting here is that this, it never hits the x-axis. It never gets to a y value of 0, but it does get really, 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 really close to it. And so that y value of 0, the x-axis, is the asymptote. Asymptote. And I love that word. It's such a hard word to say in a way. It's a fun word. It's the asymptote. I love that there are so many not vowels. What's the word? My goodness, my brain just lost it. Anyway, there's so many of them there. So yeah, there's an asymptote, and that's an important idea when it comes to exponential values. So let's see. Consonants, that's a word. Just needed to not think about it for a minute. So then a bunch of the work in this lesson then is looking at how to rewrite equations like this with no with no number here in the exponent. So how would we rewrite this so that there's no number in the exponent? Yeah, good. Nice job. So it's going to be 5 times 3 squared, and then that's going to be raised to the power x. And 3 squared, what is 3 squared? 3 times 3. Yeah, 9. So it's 5 times 9 to the power x. Good. All right. And so that's kind of what a bunch of this is looking at then in the work here. Let's see. It's funny because I think that's like the least interesting part of all of this, but you know. Do you guys have any questions? Okay. Okay, here's another example where they were talking about a population of bacteria. So a culture or something like that. So a research doctor is studying the effects of a new antibiotic on bacteria. He measures the amount of bacteria daily and notices the numbers of decreasing at a rate of 35%. So decreasing. What does decreasing tell us about the function? We're going to have subtraction. It's going to be a decreasing. So instead of an addition between the 1 and the rate, it's going to be a subtraction between the 1 and the rate. And this population began with 7,000 bacteria. And so how are we going to write the function? Well, f of x is equal to, what do you think? So the beginning value is 7,000, the starting value, that's the y-intercept. Good. And then we have 1 and then subtract, because we have a decreasing function, that tells us it's got to be a subtraction. Here I can highlight these other values. The 7,000 is right there. And then the 35% tells us that this is going to be 0.35. Right there. And now it's going to be to the power, and they often use t for time as well. Doesn't really matter one way or the other. And in this case, it's daily. Okay. So once we have that, we can rewrite it, of course, as instead of 1 minus 0.35, we can have 0.65. And sometimes I'll put this 0 in front of the decimal. Sometimes I won't. Doesn't really matter. It's the same thing. How long do you think it will take to kill all of the bacteria? And how would we find out? What would killing all of the bacteria mean in this? Oh, I did something kind of weird here. This should be t, not x. Under 10 days, there will be an asymptote, always an asymptote in exponential functions. So let's have a look. So we can put in t here if we want to. And we can change this to 7,000. And then our multiplier, or the base, is 0.65. And then we'll need to change this to a t. Now, after 10 days, there will still be 94 bacteria. Okay. So we can see that if we're starting at 7,000, that it goes down really fast at first, but then down here it starts getting slower. So what number should I try next instead of 10 days? it is decreasing by a pretty fast rate. So try 100. All right, let's see. Oh yeah, that looks like it, because this is 10 to the negative 15, which means we need to move to the left 15 places. So definitely after 100 days. So somewhere between 10 and 100. 40. Whoops. So smaller than 1. So between 10 and 40. Let's try 20. Down to 1.2. Okay, what about 25? Well, so right there. So at 20 days, there's 1 left. At 21 days, there's less than 1 left. You can't have less than 1 of a thing like bacteria. So 21 days, it looks like. All right. Well, should we keep going? Let's see, where are we at here in the lesson? I think we're at the end of the lesson. And you guys have done a good job. You want to ask any questions?